All right, let's get started. Hope everybody enjoyed their, longer weekend. Back into the swing of things with concrete design. Just a quick heads up on some announcements. Don't forget, okay, that's a typo. I apologize. This homework is due on Friday. Sorry. It's the homework in steel that is due on Monday. Sorry about that. Homework in here is due on Friday. I did have a couple announcements. One of them is in regards to capstone for next year. So I wanted to make sure that everybody's aware of how that works. In order to qualify for capstone, you have to have a series of courses, you either have to have already completed a certain list of courses, or next semester you have to be concurrently registered for them. And we have 4 breadth and 1 design, or 3 breadth and 2 design. And so you either have to have already completed those courses or currently be registered for them. So what I do is this: I basically pull every student that we have in the civil engineering program, and I do a big analysis, and I say, okay, if you want to be in capstone next semester, you need to make sure that you're currently registered for foundations or highway or something like this. And so I'll be sending basically these like individual emails soon, just to let you know. But 452, you don't have to register for 452. We'll register you ourselves because the prereqs are a little complicated. So just expect an email from me soon. We'll make sure that you're squared away. Another thing I'll go ahead and point out, I think some of you might be helping with this. I'm not sure. I'm not sure if some of you are aware of Dr. Bryce's service project that he might, or I don't know if he's mentioned that to some of you. He has a service project going on Friday where they're going to be doing some cleanup and restoration for a cemetery in the area, and that'll be taking place all Friday morning. And so if you want to go, I've decided to grant anybody that wants to go an excused absence, so I won't count you off with absence. But that doesn't mean that I show up in concrete and there's 4 people here, and Dr. Bryce said only 3 of them, the people that were absent, showed up. So I am going to make sure that y'all were there. But we are still going to have class. Okay, so class is still going to go on tomorrow. But anybody who wants to do that community service project, I'll give you an excuse absence. So I'll let you say that. Sound good? All right. Before we jump into material today, y'all have homework due on Friday. Does anybody have any questions about the homework assignment? Everybody looked at it? I hope you've looked at it. Is everybody good? Last chance.
What does it mean, the factored load being like, it was like 1.5D plus 2L?
1.2 plus 1.6.
Yeah. What does that mean?
Okay, so are you talking about problem 1?
Yes.
Okay, all right. So let's pull that up just so everybody's on the same page. So here's the problem, and the floor system is subjected to a dead load of 35 pounds per square foot and a live load of 75 pounds per square foot. Okay, let's take the example that we did in class. I gave you all a 20 pounds per square foot load, and based on that 20 PSF load, you all were able to determine, the force on this beam, the force on this column, et cetera, right? So with this problem, you're basically doing the same thing, but there's one added step. Instead of telling me what the response due to the dead load is, or the response due to the live load, I want you to tell me what the response is due to the factored load. So 1.2 times this plus 1.6 times this, but it's not this load, it's the reduced load. Because remember, this is the unreduced live load of 75 pounds per square foot. And so if you're looking at, let's say, a floor beam, you need to take this 75 pounds per square foot and reduce it to whatever that is, the 0.25 plus 15 over KLLAT. And so you'll take this load, so let's say if you're looking at a floor beam, you'll take this load and reduce it to whatever that reduces to. And so you'll have 35 here, and let's make up a number. Let's say from 75 it reduces to 46. I don't take that to the max, I just made that up. So 35 and 46, so 1.2 times 35 plus 1.6 times 46 equals some magic number, and that's what you distribute like what we did in the example. So that's what it means by a factored load. On problem 2, The problem asks for the factored, moment and factored shear, but I only gave you just the factored load of 60. So for problem 2, assume that 60 is the 1.2 dead plus 1.6 live. The idea was with problem 2, you didn't have to worry about factoring it because you did that on problem 1, but the difference is on problem 2, the frame itself is a little more complicated. So I figured I didn't want to test you on the same thing twice, essentially. Does that make sense? Does that answer your question?
Yeah.
All right, is everybody else okay with that?
I got a question kind of in the future.
Yes, sir.
We didn't really, since it's a simply supported beam, we didn't really go over like the WL squared over 8 a
Okay.
whole lot. We like found the resultant forces.
Yeah.
Does it matter which way we do it? Like, do you want us to go through everything? And
That's a great question, and the answer is no. I mean, I don't really care whether you, so like in structural analysis, we would take that beam and actually draw the shear diagram and draw the moment diagram. Let me show you something, okay? So I just want to make sure that everybody's aware of where that comes from, okay? So here's a beam. Let's do it like we did it in structural analysis. Okay, so we have some load on it, right? The beam is L long, right? And so what would we do in structural analysis? We would collapse that into a single load that's WL, right? And so half on this side, half on that side, so that's WL over 2, WL over 2. Is that right? And so what does the shear diagram look like? Well, we go up WL over 2, down like that to minus WL over 2, and then back up, right? Okay, so let's look right here. What's the area of that triangle? Help me out. Like, what's the area of a triangle? 1/2 what? 1/2 base times height. So the area of 1/2 times the base times the height. So what's this dimension?
L over 2.
L over 2. And what's that dimension? WL over 2, right? So if I calculate that out, the top is 1 times L times WL, WL squared. The bottom, 2, 2, 2. 2 times 2 is 8. So your moment diagram is a lot to a little to a lot, WL squared over 8. So all that WL squared by 8 is just the maximum value on your moment diagram if you carry the whole thing out. So if you want to do the analysis on paper, you can. If you want to use WL squared over 8, that's fine too. You'll get the same answer. You should get the same answer. If not, then you probably got like a calculator issue there somewhere. Did that answer your question? Or?
yeah.
Okay. I want to make sure that's clear. I did kind of gloss over that a bit, but that's sort of the purpose of that guide, is to sort of save you from having to do all of that. And all of those shortcut formulas are doing that. They're just taking common loading scenarios and saying, okay, if my situation matches this common loading scenario, I don't have to go through the process of drawing the moment diagram. I can just plug and chug here, and that will tell me what the value is. So the big thing to keep in mind is that if you're going to use that guide, which is fine, that's why I gave it to you, just make sure that your loading scenario matches the formula. So for instance, this is a simply supported beam. Simply supported beam subjected to a uniformly distributed load, maximum moments WL squared over 8. But as soon as it becomes a cantilever beam, or instead of a distributed load, it's a point load, then the formula changes. So don't just, oh, well, it's WL squared over 8 because that's what we've always been using. No, we're using that formula because it matches that loading scenario. As soon as the loading scenario changes, the formula becomes useless. Okay? Does that make sense? This is why, please, if there's any other questions, I really want to make this, yes, go ahead.
On problem 2A, where
2A.
you're determining the maximum factored moment on an interior floor beam, which beam is that you're talking about?
Any one of these interior beams in this bay.
Okay.
Yeah, because whether or not you're looking at this beam, or this beam, they should all be the same.
Okay, that's what I was thinking. Just want to make sure.
Yeah, any one of those interior floor beams. And for problem B, I want to know the maximum shear on this girder. And so that one's a little more involved because you've got beams framing into it. Yes, sir.
For part C, do you just take the load on the column and multiply it by 5?
Well, yeah, but you have to determine the load on the column for a single story.
Once you get that, you just multiply it by 5.
Yes.
Okay.
Yes. But again, like you have to, so you figure out the tributary area for that column and then so on and so forth. And the same thing with problem one. The problem one had 6 stories, so you can multiply it by 6. Now, in reality, there's only 2 instances where you would never do that. The first is always, the floor loads are different than the load on the roof. The roof has a different load. So if you had a building that was just one big box that was all prismatic and every floor looked the same, then you might have, I'm just making up numbers, you might have 70 kips, 70 kips, 70 kips, 70 kips, 40 kips. The roof load's usually a little smaller because it's different loads. You don't have live load, you have snow load, things like that. And then number 2, that method would be fine if all of the stories were identical. As soon as you have a building like, I don't know, maybe like Drinko, where that doesn't look the same on every story, then you'd have different loads on every story. But other than that, yeah, that's what you would do.
Okay.
That's a great question. Any other questions? This is good stuff. Y'all feel a little better about it? Everybody good? Bless you. All right. I want to start getting a little bit into concrete today. What we've done for the past couple of days is discuss, and if you're in steel design as well, it's probably started to bleed together a bit because we've used a lot of the same load combos, the same concepts. We've just been talking about different force effects. And here we've been talking about gravity loads. In steel, we've been talking about lateral loads. But in the end, we have these 5 load effects: dead, live, snow, wind, and earthquakes that structures need to be strong enough to resist. And I think we closed last time looking at our LRFD load combos, the 1.4 dead and the 1.2 dead plus 1.6 live. I don't want to spend a whole lot of time focused on this right now because, believe me, we're going to have more than enough experience throughout the semester looking at these load combos. Instead, today, what I'd like to do is go into concrete itself. Now, what we're going to do today is we're going to discuss some behavior and some basic material properties that you need to know and understand associated with concrete and with reinforcing steel. And then we're going to start to get into beams, okay? So the way this class works, we're going to spend probably if you're talking about a building, a reinforced concrete building, because that's really what we're sort of focused on in this class is buildings and those types of systems. There's really only 2 types of elements that you're going to be looking at. Flexural elements like beams and slabs, and axial elements like columns. If you can design beams, columns, and slabs, that's reinforced concrete design. So today we're going to discuss some basic material properties that we're going to use throughout the semester, and then we're going to spend the vast majority of the semester looking at beams, because whether we're looking at shear, at moment, at deflection, whether we're looking at T-beams or doubly reinforced beams or slabs, it's all flexural elements. So we're going to spend a lot of time on that. So first off, let's talk about material, and I'm just going to take it 2 parts. We're going to talk about concrete, and we're going to talk about steel. Now, I'm just curious, how many of you have had 321, the civil materials lab, where you test the cylinders and all that? Some of you might have, some of you might not have. If not, that's okay. If you have had the course, then the next 5 minutes are probably going to be fairly repetitive from what you learned in there. And if not, I'm just basically showing you what all you need to know from there. If there's any one statement or sentence or phrase that I want you to remember from this course, concrete is a material that behaves very well in compression, and it behaves very poorly when it's in tension. In other words, if I have a piece of concrete in my hand, and I take that piece of concrete and I push on it, I push it together, concrete loves to experience compression. But as soon as I take it and I yank on it, it'll fail. I always joke, all of the specs and the various classes of concrete, all that's a bunch of lies because there's only 2 types of concrete in this world, and that's wet and cracked. That's a joke, but it's really not that far off. Concrete is a material that behaves very poorly in tension, and when it's in tension, it likes to crack. To give you an idea of some numbers, if you look at normal weight, regular, everyday concrete, it usually has a compressive strength of around 4,000 psi, but its tensile strength is something like 450 psi. It's very low. It's anywhere between 8 to 15% of its compressive strength in tension. So that's why we put reinforcement in concrete. The whole point of putting reinforcement in concrete is to arrest cracks and regions of tension. That's reinforced concrete design in a nutshell. So that's, spoiler alert, that's what we're doing. So I want to talk a little bit about this. Now, if you were in 321, I guarantee you all did this, right? Did your cylinder test, cast your 4-inch cylinders and failed them at 7, 14, 28 days. If you haven't had 321, this is arguably one of the most fundamental lab tests that civil engineers perform, and that is the assessment of the structural behavior of a sample of concrete. Unlike steel or even wood or some other civil engineering materials where the properties are either lookups or they're verified by somebody else, like for instance the mechanical properties for steel are usually just, I mean, when you buy grade 60 rebar, you know what the yield stress is. With concrete, you have to evaluate it. That means performing regular testing. One of the tasks that you will learn in CE 321 is, okay, I have a project and I need to design a batch of concrete that will generate 5,000 psi in compressive stress. So you will learn how much aggregate do I put in there, how much gravel, how much sand, how much cement, how much water, what are the proportions that I put in there in order to generate that mix. And that's what you do in 321. And here we say, okay, if I've got a batch of 5,000 psi concrete, how do I proportion that, for a beam and a column in a building? And so that's sort of the idea behind what we do in here. So all I really need you to understand is just what a cylinder test is. One of the most common tests that we perform for a sample of concrete is to cast a cylindrical specimen and just press it until it fails and record its response. So if you remember from Engineering 216 from deformables, stress-strain relationships are very important to characterize materials. And these are some typical stress-strain curves for concrete. I don't expect you to be, to remember everything that was quoted in every lecture in Engineering 216, but there are some facts and parameters that I think you need to be aware of. One of the things about concrete is it's a material that is very non-linear in nature. And so what do I mean by non-linear? Everybody in here had Engineering 216, and whether you remember it or not, or depending upon how much your professor emphasized this, everything that you do in Engineering 216, and even everything that we did in structural analysis last semester, we assumed linear behavior. And the best way to understand linear behavior is to think of a rubber band. So the way a rubber band works, you have a rubber band in your hand, you take that rubber band, you stretch it, okay? You've applied load to that rubber band because as you stretch it, it wants to push back on your hands, and then you've moved it through a displacement, so you've applied load. Now as soon as you let that load go, the rubber band snaps back to its original shape. So it deforms proportional to the load that you put on it, and it snaps back to its original location. So that's linear behavior. It just sort of goes back to square one. Concrete is a little different. The best way to describe how concrete can behave is, that's kind of a little bit of a gross example, but imagine if you had a piece of chewing gum in your hand, like a big old piece of really big chewing gum, like Bubblicious or something. And you had it in your hand and you squeezed it, and then you let go. It wouldn't snap back to its original location. That depression would stick. It would stay there, right? Well, that's nonlinear behavior. That's it accepting those deformations and staying. It's also akin to what you would do like with a Coke can. Like if you had a Coke can in your hand and you crushed it, when you let it go, it doesn't snap back to its original shape. It remains crushed. That's nonlinear behavior. Another thing is that you'll see that depending upon the type of concrete that you're looking at, you can achieve various maximum compressive strengths. So you can have some concrete that's designed to just generate 1,000 psi or 1 ksi, and then you can have concrete batches that are designed to generate 6,000 psi. There are trade-offs to these various mixes. Usually concrete that is stronger, that can resist more compressive strength, is also a concrete that is less ductile. So the stronger the concrete, the less the ductility is a common trade-off. And you can tell that here because the curves with the low PSIs or stresses are sort of trailing off the graph. But as you get these really large stresses, they're just not able to accept much deformation. It's sort of like it gets so strong, it also gets kind of brittle. So it's not able to stretch and absorb that load. which can be important, for instance, if you're looking at seismic applications. Ductility is a really, really important aspect. Ductility is just the ability to withstand all those deformations. Arguably the most important number that we're after with a batch of concrete is its compressive strength, or in other words, the absolute maximum compressive stress that it can achieve. And we use compressive strength all throughout this course in order to design and detail beams and slabs and columns and what have you. We denote that with the term FC prime. So FC prime, I just wrote some terms up here on the board. One of the things about this course, and this is also true in steel design, is that we really try, as structural engineers, we really try and do a pretty good job of using consistent notation across the board. So FC prime is compressive stress. It is always going to be compressive stress. I'm not going to one day come in and say, X sub 3 is going to be compressive stress today. No, FC prime is always going to be that. When I use the term B, B is always going to represent a beam width. When I always use the term H, it's going to represent the beam height. The term D is going to be the beam's effective depth. Those symbols and terminology, we're going to build on that throughout the semester. So some of these terms here, we're going to see them again and again, and they're going to keep popping up. Like for instance, I have got this term lambda here. We're going to see this today, and then we're going to see it, a few weeks from now when we look at shear and so on and so forth. So just keep in mind this notation we'll build. Now, so like I said, concrete's a very nonlinear material. It doesn't have a linear region like steel. We do need to define an elastic modulus. So remember, one of the most fundamental equations in 216 was stress equals E times your strain. Remember, E was your Young's modulus or your Hooke's modulus, and each material has a unique elastic modulus. So the elastic modulus for steel is 29,000 KSI. The elastic modulus for aluminum might be something like 10,000 or 12,000 KSI. For concrete, that elastic modulus can change dependent upon the type of concrete that you're looking at. But basically what we're saying is, if I've got a given graph like this, the elastic modulus is sort of basically the slope of that region right here. So I know that's not really a straight line, but you can think of that as your Young's modulus, the slope of that line. So that slope of that initial line is going to change depending upon if I'm looking at 6 KSI concrete or 3 KSI concrete or what have you. So we actually calculate it based on whatever type of concrete that we're looking at. Now, here is the expression that we use to compute the elastic modulus for concrete. We have two equations, and I'll tell you that by and large, the second one is the one that we're going to use most often, and we will use this periodically throughout the semester. I need to sort of deal with something right now that's going to pop up, okay? Now, for those of you who make sure that you're really cognizant about making sure that your units match, which should be everybody in the room, these formulas don't really make a lot of sense. In other words, your compressive stress, your compressive strength is a stress. It's usually like a PSI or a KSI or something like that. Well, your elastic modulus, your Young's modulus, is also expressed in units of stress. It's like a PSI or a KSI or something like that. So the question is, how in the heck do you take a square root of PSI and get a PSI? That doesn't make any sense, okay? I'm going to tell you, I know it doesn't make sense, but that's the way it is, okay? And let me explain why. I mentioned this a bit, I think, in steel design, but in case I mention it here, I'm going to say it again. We tend to deal with two types of equations when we talk about real-world, real-life engineering. One of those are mechanistic equations, so these are the ones where you can derive them using some calculus and a Newton's second law or something like that, and that's sort of akin to everything that we did last semester in structural analysis. I mean, it was forces and moments and deflections, and we could basically derive all of that stuff and get to X equals 4. That's a mechanistic equation. An empirical equation doesn't really work like that. An empirical equation is this. Let's go down to the lab and let's bust about 200 cylinders. And let's see if we can look at the compressive strengths and look at the value that we're trying to compute, and is there a way we can curve fit an expression that's easy to use? And that's this, okay? So sometimes they don't, the units don't quite work out, or the mechanics look a little weird, but I'm telling you that this equation is very, very accurate in predicting this. Now, this is not the first time that we are going to see a square root of FC prime, okay? And we'll tell you right now, this is how it works, okay? Whenever you see a square root of FC prime, I want you to sort of remember this. You put in PSI, you get out PSI. Now, I wrote that on the board because everybody in this room should write that down, okay? Because I guarantee you, somebody in here is going to mess that up, okay? Don't worry, we're going to have some examples where we explore that. But anytime you see a square root of FC prime, you need to make sure that your stress units are in PSI, because you'll put in PSI and you'll get out PSI. It's very easy to have an FC prime in KSI and just go, oh, it's the square root of 4, and the units will not work out, okay? So that's just something to keep in mind for now. Now, there's two different formulas. One of the formulas is for normal weight concrete. The other is for pretty much any concrete. So think as the weight of your concrete changes, you can get different material properties. Most of what we're doing is normal weight concrete. There are instances where, as a structural engineer, you really might want to decrease the weight of the structure, either for just trying to improve the design. Maybe you're trying to reduce it for seismic demand or whatnot. But more often than not, we're going to be dealing with normal weight concrete. And so basically just all you need is your FC prime, and you can compute your Young's modulus. We'll be using that equation very soon. Now, as stated, concrete is a material that behaves very, very well in compression, but it behaves very poorly in tension. If you look at the math, tensile strength of concrete is somewhere between 8 and 15% of its compressive strength, so it's pretty weak in tension. There's a couple of ways that you can measure tensile strength. You all did this in 321 probably with the beam test, when you cast a beam of concrete and tested it to failure. And if you did the math, the stress where it failed was a lot less than when the cylinder busted, okay? There's a couple of ways that you can do that in the lab. You can do the beam test. So you put a beam in the lab in 4-point bending and just compute the stress. If you ever want something that's fun to do in the lab, one of our students did this. They drew a heart right here to see if it would crack right through the heart. I thought that was kind of fun. It's the first time I've ever seen it. I was like, oh, that's kind of fun. Another way that you can test FR is to actually test the cylinder on its side and figure out and record its crack there. That isn't done as often as just the beam specimen, but it is another way of doing it. But what you need as engineers are a means of predicting it, okay? So the way that we can predict the modulus of rupture is with this expression here. So if FC, so think about it like this. If FC prime is the maximum amount of stress that concrete can experience in compression, FR is the maximum amount of stress it can experience in tension before it cracks, okay? Now the way that we compute that is we compute that as 7.5 times lambda times the square root of FC prime, okay? Now lambda is a lightweight aggregate factor. Basically the idea is if you're using a concrete mix that's lighter, it's more susceptible to cracking, so we would reduce its modulus of rupture. One of the other things that I'll go ahead and mention now, and this is something you'll probably just want to get used to throughout the semester, one of the things that you'll find in concrete design and steel design and what have you is a lot of times, and I think it's particularly true in concrete design, but you'll have an equation and then you'll have a bunch of factors adjusting that equation for various conditions. And in most normal circumstances, a lot of those factors are 1. Usually you're adjusting your equation because something's different. Like in normal everyday instances, it's 7.5 times the square root of FC prime. But if you've got lightweight concrete, well, then you take that lambda value as 0.75 or something like that. Now, one of the things I did sort of gloss over in the beginning or beginning of this lecture, I mentioned this at the beginning of the class that we're designing everything according to ACI 318. I screen captured some of these tables out of ACI 318. So these tables basically tell you what lambda is under various circumstances. So if you're dealing with a concrete that has a unit weight less than 100 pounds per cubic foot, then your lambda is 0.75, which is a really, really light concrete. Most of our concretes are normal weight, so usually like 140, 145 pounds per cubic foot, and in any of those instances, lambda is 1. In most cases, lambda is going to be 1, but if we're ever dealing with a lightweight concrete, lambda is something that you need to determine. So it's just something to keep in mind. But your two most common values are either 1 for normal weight concrete or 0.75 for lightweight concrete. If you have sand lightweight concrete, which basically just uses different proportions of aggregates, then you can use a lambda value of 0.85. But all that's here, and if you have a problem on a homework or an exam where you need to use a different lambda value, you'll know, okay, it's lightweight concrete, so I need to use this. So it's not something that you'll just be, oh, I don't know what value to use. You'll have an idea. Any questions? I know that seems like a lot of formulas and details. Don't worry, we take our time with employing them. We ease into that. I don't really have a lot else to say right now about concrete. I do want to talk, however, right now about steel. Okay, this is reinforced concrete design. So in here, we need to have a good understanding of how concrete behaves, but we also need to know a little bit about how steel behaves. Now, the two most common types of reinforcement that we use in reinforced concrete are welded wire fabric, which we really won't talk about very much because most of the designs that we do in here, we're talking about designs for loads where welded wire fabric really wouldn't be enough. Welded wire fabric is basically used for like some slab reinforcement, some temperature shrinkage reinforcement, usually nothing that for load carrying capacity. It's just sort of your secondary stuff. The big one's rebar, okay? That's our big reinforcement that we're really interested in. First thing I want you to know about steel is its Young's modulus, how much it stretches in proportion to how much load you put on it. There are some numbers that as civil engineers you just need burned into the back of your head. Like the unit weight of water is 62.4 pounds per cubic foot. That number just needs to be burned into the back of your head. The Young's modulus for steel, 29,000 KSI. That number needs to be burned in the back of your head. You will memorize that number by the time you get out of here. I promise. We will be using it quite regularly. 29,000 KSI or 29 million PSI. That number stays the same regardless of grade, whether you're dealing with rebar or structural steel like A36 and 992. The Young's modulus for structural steel is always 29,000 KSI. You can set your watch by it. What does change, however, is the yield stress. So remember, so let's go back to the Coke can analogy. I take the Coke can in my hand and I start applying load. If I barely press it, if I just sort of press it a little and then let it go, it sort of snaps back to its original location. Like I have this can here, right? I have this can. If I take it and I press it a little and let it go, it goes back to its original shape. That's linear behavior. Now, if I were to take this can and wrench on it, I'd make a mess because it's still got stuff in it. But if I were to take this can and really wail on it, it would deform permanently, right? And the reason why it would deform permanently is because the stress would exceed the yield stress. So the yield stress is when those deformations start to become permanent. And that does change depending upon the type of grade. Fortunately for rebar, it's really, really easy to know what the yield stress is. It's just the grade number. So if I'm dealing with grade 50 rebar, the yield stress is 50 KSI. Arguably the most common rebar grade that we will deal with just as civil engineers, let alone in this class, is grade 60. So grade 60 rebar, so a yield stress of 60 KSI and an FC prime of 4 KSI are about the most common material grades that we will deal with, not just in this class, but in civil engineering practice. Sound good? Now, let's talk about rebar size. I'm not sure if you've been exposed to this in 321 or not, but I want to make sure that everybody is aware of how rebar is sized. So you've got rebar that's like this, and it can be anywhere from about this big around to about like that big around. And it depends on basically your rebar number. So there's number 4 rebar, number 6 rebar, and the number will tell you the size of the rebar. The rebar comes in sizes from number 3 to number 11, so 3, 4, 5, 6, 7, 8, 9, 10, 11, and then rebar number 14 and number 18. Now, as for what those sizes mean, if you're dealing with a rebar that's anywhere between a number 3 and a number 8, you can take the number, you can divide it by 8, and it will tell you the diameter, okay? So rebar's circular cross-section. So if I have number 7 rebar, okay, 7 divided by 8 is 7/8 of an inch. It's 7/8 of an inch in diameter, okay? So if it's number 6, 6 divided by 8 is 3/4, it's 3/4 of an inch in diameter. So if you know that, you can know the cross-sectional area and all of that. Number 9s, we use number 9s a lot in here. Number 9s have a cross-sectional area of 1 square inch, okay? It's really easy to design with them, because if you're doing a problem and you need 6 square inches of steel, use 6 number 9s, you know, it's really easy. Number 10, that's just the one where the diameter and the area equal one another numerically, and I'll show you that here in a second. Number 11s are equivalent to a bar that's 1 1/4 by 1 1/4. Number 14s and number 18s similarly. If you go to the next slide, this shows you like a more numerical breakdown of everything. So if you're looking at, let's say, a number 5, 5/8, or 5/8 is 5/8. So it's a diameter of 0.625. The area of a circle that has a diameter of 0.625 is 0.31, and that's how much a number 5 weighs, about 1.04 pounds per foot. So in case you need that. I'll show you something on Blackboard. If you log on to Blackboard, I've actually if you go into design aids, I've isolated this slide so that you would just have a slide just on the rebar size. And I also gave you this. So I have this slide, and then I have this. This is a design aid that we're going to use this semester pretty prevalently when we get into design mode. But what it does is it delineates the area of different multiples of rebar. And we'll need that when we start designing beams and so on and so forth. We have one for beams, and then we'll have another one later for slabs. That's why the beam is underlined. So if I have, let's say, 9 number 5s, the area of all that is 2.76 square inches. And so it helps out when we're in design mode. It's all sort of listed here. I'll give you a hard copy when we start getting into design mode. I just wanted to make sure you all, were aware that was up there. Sound good? Okay, so that's up there, and then I also isolated that one slide as well. Okay. Lastly, I just wanted to mention a little bit about welded wire fabric. Again, we really won't use it very much. It just I just wanted to show you the way it's sort of delineated. So it'll be delineated like welded wire fabric, 6x12 and then 16x8. The 6x12 tells you the spacing, and then the 16x8 tells you the area of each of those wires. I just wanted you to be aware of it, but to be honest, we really aren't going to use it very much in here because, again, we're talking about some very significant load events, and welded wire fabric really isn't necessary, or it wouldn't even be sufficient for what we're doing in here. Any questions? All right. Let's get into some fun stuff. Let's talk about some actual stuff related to concrete design. Okay. So like I said, the first thing that we're going to do in here is we're going to talk about the beams, flexural elements. In other words, I take a beam like this, okay, and I start applying load, and I start asking how much load can this beam withstand before it fails, okay? And the term failure it's a little vague right now. So I'm not really going to talk so much about failure right now. Instead, I really sort of want to look at this from a behavior perspective. In other words, how does this beam perform as the load increases from hardly anything on it until it's literally any more load that would kill people. So we're going to consider our discussion for a very, very basic beam. And the way I like to describe this is I argue that there's really 3 stages of beam behavior, okay? So first stage is the region that I'm calling the concrete uncracked stage. In other words, the concrete beam is really not seeing very much load. It's very lightly loaded. And so it behaves much like a beam of any other material. The concrete regions in compression and tension are behaving largely the same. And that will continue until the concrete cracks. Now, like I said, there's only two types of concrete in this world, and that's wet and cracked. So if I have a concrete beam and it's cracked, does that mean that's it, that it cannot resist any more load? Absolutely not. The reason that we put rebar inside a concrete beam is to arrest those cracks and to begin carrying the load once the concrete gives up. Keep in mind, when we're talking about beams, they're being bent, right? You're taking this beam and you're bending it. So part of the beam is experiencing tension, but the other part is experiencing compression. Once the concrete beam is cracked, we assume that all the region that's experiencing tension is doing no good. That's where the rebar takes over. But the part of the beam that's experiencing compression is doing just fine. So once the concrete cracks, the steel takes over. And so you have this second stage of behavior where the concrete's cracked, but it can still carry load. And that will continue until you reach the beam's ultimate capacity, which is stage 3. That's when the steel has fully yielded, the concrete has reached its full compressive capacity, and that beam is done. Okay, and so we'll take it one step at a time and see how this behaves. So like I said, stage 1 is the concrete uncracked. The beam is somewhat lightly loaded. The tensile stresses are lower than the modulus of rupture. The entire cross-section is resisting bending, so you got compression on one side, tension on another, and that will continue until the beam cracks. Now, when does the beam crack? Okay? Well, the beam cracks when the region in tension hits FR, hits the modulus of rupture. Remember, the modulus of rupture, this is the stress at which concrete cracks. Okay? That's, when I use the term cracking moment, that's what I'm talking about. The part at which the extreme tensile fiber reaches FR. Now, this formula right here, if it looks like it came out of nowhere, it really didn't. Okay? From 216, do y'all remember this? One of the most fundamental formulas in deformables. If you have an element that's being bent, this formula will tell you what is the stress due to bending. And it's a function of really 3 things. The amount of moment that you're putting on it, the moment of inertia, and how far you are away from the centroid, right? And so all this formula is doing is saying, okay, I know what the stress is, so if I take this formula and solve for the moment, it's the same thing, right? A stress times a moment of inertia defined by a distance. That's all this is, okay? So we have our modulus of rupture, which is the stress at which we experience cracking, the gross moment of inertia, and so if you're having a hard time remembering what that is, don't worry, we'll have experience on that. And then we have the distance from the centroid. So this is actually probably going to bring it back to a little bit of 216, probably even bring it back to a little bit of statics, because we're going to talk about centroids and things like that. I have a little bit more of a straightforward, direct way of computing it, but don't worry, we'll take our time with it. Sound good? All right, let's get some math at least started. We probably won't finish this example, but we'll at least start into it. So for the beam shown, I want to compute the bending stress at the bottom of the beam for a moment of 25 foot kips. And I also want to compute the normal, if I'm using normal weight concrete with a compressive strength of 4,000 psi, I want to determine the cracking moment. Okay? So a couple things about this beam. I have a concrete beam, so when you see an image like this, what I'm talking about is I've got a beam that's however long, and I'm samurai sorting or lightsabering through the beam, and I'm looking at the cross section. So I have a beam that's 12 inches wide and it's 18 inches tall. Now, if you look at the beam, you'll notice that the rebar is in the bottom, right? I have a beam, I'm standing on top of it, so I'm bending it like this. The bottom is experiencing the tension. So your reinforcement should be near the bottom. Top's in compression, bottom's in tension. So that's one thing I want you to notice. Another thing I want you to notice are the symbols that I'm using. So I'm using B for the beam width. I'm using H for the beam height. Okay? I will always use those symbols throughout the semester. Okay? The other symbol, which actually we won't directly use for this example, but I did want to throw in, is this term D. This term D is the beam's effective depth. And it's from the tippy top of the beam to where the rebar is, to the center of the rebar. Okay, that is a very important term that we're going to be using throughout this semester. So that term, while it's not relevant to this problem, it will become very relevant throughout the semester. Finally, the reinforcement. I actually won't need the reinforcement for this problem, but I have it in here. This beam is reinforced with 3 number 9s. Remember, a number 9 has an area of 1 square inch. So that's 3 square inches of steel in this beam. Sound good? All right. Let's at least get a couple things computed and then we'll call it. So, ooh, that's big. Okay, so now let's jog the memory banks a little bit. Does anybody remember how to compute the moment of inertia of a rectangle?
It's been a minute.
Been a minute, right? I'll give you a clue. BH cubed over, there we go, BH cubed over 12. That's a formula you might want to remember, okay? Now, I'm going to term that, actually let me move this down here. I'm going to term that the gross moment of inertia. All right, so that is IG, so that's BH cubed over 12, so that is 12 inches times 18 inches cubed over 12. And so what does that equal?
Inches to the fourth.
Okay, 5832 inches to the fourth. Do I have a second on that?
Yep.
Okay. Now, before we move on, I'm curious. How many of you, if I were to actually look at what you wrote right now, just did this? How many actually didn't write the little I and write the little n? As a piece of advice, write the little I and write the little n. And here's why I say that. We're going to have, I'm not going to do that, but we are going to have some problems and some equations where we really start mixing up the units game something fierce, okay? And it's really easy to get your units in a bind. And so I really want you to get into the practice of actually writing it out. You can use shorthand, use a little double ticks for inches, that's fine. But get into the practice of actually writing it out. I'm telling you, you will save yourself some headache down the line. Because you're going to see it here in a second, how the units are going to get a little wild. You probably won't see it today, we'll see it on Friday. Okay. Now, we're going to do one more thing, and then we kind of got to call it because we don't have time. Don't worry, we'll explore this example next time. Here's the rectangle. Where's the centroid of that rectangle? Like from the bottom, how far up till I get to the centroid?
In the middle.
In the middle. And so from the top, or from the bottom, how much is that?
9.
9 inches. So you'd say the centroid is about right there, right? Okay. I'm going to call this distance YT. YT being, and what I'm going to call that, the name, I'm going to use extreme fiber distance. And if you want, you can say tension. In other words, how far is it from the centroid to the very, very, very tippy top or the very, 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 very bottom, okay? And those quantities are important for later when we're looking at stresses. So the extreme fiber distance and tension, I'm going to call that YT. And so the formula that I would use to compute that is H over 2. So 18 inches over 2 or 9 inches. Now, the only reason that's the case for this problem is because I'm dealing with just a rectangle, okay? We're going to have a T-beam later where it's not going to be just H over 2. You're actually going to have to figure out where the centroid is and do a little bit of figuring there. So for now, we can just keep it simple, but we'll ratchet it up in complexity as we move on. Now, we're running out of time today. What we're going to do next time is we're going to jump right into it as soon as class starts. We're going to compute the cracking moments, see whether or not this beam is cracked, compute some stresses, and then we're going to start ramping it up with a more, I don't say difficult, but a more involved cross-section where we got to do a little bit of that. Does that sound good? All right, well, if you're not in SEAL, I will see you all on Friday. Otherwise, I'll see you here in a few minutes. That's all I got.